So, welcome back to our class, and today we are going to continue our discussions on the Gaussian square quadratures. And so let's first take a look at what we have already found out last time. So wait. Okay, so last time we have we got one important theorems, and then that theorem tells us that so we got one important theorem, and that theorem tells us that if we have n nodal points, so if we have n nodal points, and for the we can have we can have at most 2n-1 degree of precision for the quadrature rule. And this is something very important result, and then we can make use of this to create the Gaussian quadratures for the quadrature rule, any quadrature rule. And so with this theorems, and then with this theorems in mind, and then we want to create one quadrature rule that we can achieve the highest degree of the precisions. And last time we also talk about one example, and then at that example zeros, and then we says we have two nodal points, and then we want to create that Gaussian quadrature rule by finding the we look for the C1. We have 4 variables here: C1, C2, X1, X2, and then we look for this 4 value such that this quadrature rules had the highest degrees of precisions. And because we have 2 points, and then by the first theorems, and then for the this quadrature rules, it can have at most 2 times 2 minus 1, that is the 3 degrees of precision here. So we do some kind of we plot in the fx equals to 1, fx equals to x squared, and then up to x cubic, because we have 3 degrees of precision here. And then so we do substitutions into this formula, and then and we got an equations, a system of the equation, and so forth: C1, C2, X1, X2. And this is the first examples we have. And this is how we get the Gaussian quadrature rule for one concrete example. But for the general theory, general theories for the quadrature rule, the Gaussian quadrature rule, we want to derive it in this way. So for the Gaussian quadrature rule, this is the general one, quadrature formula, and then the first one. So the important things in the Gaussian quadrature rule is to look for the positions of the xn, the nodal points. So first of all, we need to get the x0, x1. Let's say we are going to use the index starting from 1, x1, x2, and then all the way to xn. If we have n nodal points, and then we can expect that we can have 2n-1 degrees of precision here. And for the nodal points, how can we find out the nodal points? We have n nodal points here, and then we solve the nth Legendre polynomials, and so we get the roots, because this is the end Legendre polynomials. The nth Legendre polynomials is with degree n, and it has simple real roots. Simple, it means that it would not be repeated. And then real roots, it means that each root is real number. We don't have a complex number here. And then I have attached the links to answer these questions, why this is simple, why this is all the roots are real on the canvas. This is something extra, and then you don't need to know if you are not interested into the fact of the roots. So one fact about the root is that, okay, all the roots are simple, and they are real numbers. And so we have n roots here. Once we get the nodal points, these are the nodal points, right? And this is the nodal points. And what do we need to find out for the what is the remaining things to figure out in the Gaussian quadrature formula? So in the quadrature formula, it looks like this, right? And this is the general quadrature formula. Sigma I equals to 1 to the n. Let's say we have n nodal points, and then it should be the Ci and then Fxi. So we already have the xi, the nodal points, by solving the Legendre polynomials, and then we have n roots here. And then the rest of things we need to figure out is the Ci, the coefficients. The coefficients can be computed in this way. So this is the nodal points. And what about the coefficients? The coefficients is computed in this way. Ci, and then we just use the basic functions in the Lagrange polynomial, and then we do the integrations on it. So once again, I want to mention that we are approximating an integrals on the intervals -1 to 1 and the fx dx. So here we are going to use this quadrature to approximate that integrals. And then we are still working on the -1 and 1 interval. And so now let's figure out the Ci coefficients here. We can compute the Ci coefficients in this way. So we are doing the integration, and don't forget that this part is just the basic functions from the Lagrange polynomial. This is the j does not equal to I, x minus xj, and x, because we are calculating the Ci, we have xi here, xj here, and you do the integration, because this is the definite intervals over the interval -1 to 1, and then so this is a fixed number. And so now, one good news is that, so you can see that if we have n nodal points, right, and then this nodal points are the roots of this n Legendre polynomials. So which means that if you get a given number n, and then the positions of the nodal points are fixed, and also the Ci, the coefficients are fixed as well. So what can we do in this case? So if we want to use the Gaussian quadrature rules to calculate something, to approximate something, usually the practice is that we have a table. So I just say, if you have nodal points, you know how many nodal points you want, right? And then actually we have a tables of the coefficient, a table of the fixed nodal points. So on the completed lecture notes, I have already posted the completed lecture notes. Is in a typing way, and then in the completed lecture notes, there's another table, is the exact value. So if we have two nodal points, and then these are on the interval -1 to 1, and if we have two nodal points, and then that nodal points should be this two. And if you go to the canvas to take a look at the completed notes, and then this is the square root of 3/3, and then this is the negative square root of 3/3. And once again, if you take a look at this table, you will figure out that the roots are symmetric about the origin, right? So if we have three numbers and we have three node points, we have 5 node points, you will see that we have a 0 here for the node points. We have a 0 for node points. This is the node point xi, and this is the corresponding coefficients. So this means that this is what we have in the formula. This is the xi, and this is the ci. So you will see that these roots are, if we have 3 node points, we have this one, this one, this one. And you will see that they are symmetric about the origins. And for the 4 node points, you will see the symmetries as well. And so what can you do if you want to approximate? So let's take a look at the example first, because the theory is so long. If you want to prove the theory, and then it takes time, although we have already started the theorem proof last time, but let's take a look at the example, which I think most of the students are interested in, and how to use the Gaussian quadrature. You don't need to compute the roots and the coefficients each time, because usually people are looking at the table and then use the value. Because the fixed, if you know how many node points you want to use, the coefficients is fixed, and then the node points are fixed as well. So let's take a look at these examples. We have -1 to 1, and I just bring out all the things here because the value is so long. So I'm going to calculate the integrals exponential x times cosine x. So we are going to, what's the question asking? We have 3 node points, so which means that we are going to use this column, these rows here, the information is included in here. And the node points we have are, this is the first node points, 0.717 something. And then we also have the origins here. Because actually this one we have the, so this one, we just do the substitution. This is just the EX, cosine X, but in the node points over there, the first node points. And then for this one, it's actually the numbers we have. It should be the E0, because the E0 equals to 1. So it just give the writing here. This one is just the E0 cosine 0. You plug in the 0 into the EX cosine X function. And for this one, this is the third node point value. And corresponding to each node point, we have the coefficients, right? And so for the first node point, we have 0.555556. And this is the coefficients is around 0.5, and then but you can still use the whole number there. But that one is still an approximation number, but you can use more precision here from here. This is the point A, around 0.8, around 0.5, but you definitely can use more digits after the decimal points. And after you apply the quadrature in this way, so let's take a look. This quadrature is just the I equals to 1, 2, 3, and then fxi, and then we have the ci from the table as well. And this is the quadrature, and then we can look for the xi and then ci from the table. And after some calculations in the calculator, and then we get this approximation value. And compared to the true value, this is the true value. We have such an error here, and it looks good. This is the quadrature. It gives you more precisions in the approximation. Although we use only 3 node points, but you can see the results is pretty satisfying, right? This is how we apply the quadrature, the Gaussian quadrature. This one is the Gaussian quadrature. And let's go back to let's take a look, one more application. Yeah. Questions?
So this is totally accurate with polynomials up to degree 2n minus 1, right? And then if there's a non-polynomial function.
Yes, it's up to the, so we have three, we have three, you mean that three nodal points, right? With three nodal points, it is exact up to 3 times 2 minus 1, because this is 2n minus 1, yes.
But like this, the integrand here isn't the polynomial.
This is not polynomial, so
is there any bound on the error, or is it just the more nodes you have? I mean, I assume the more nodes you have, better. But
is there any bounds between the error?
Is there any bound on the error when the integrand is not a polynomial?
There's no such a thing in balance things in here. Okay. The error is just coming from the quadratic.
Okay.
Yeah. But here definitely we have some error here, because this textbook, it is using some round-off value for the coefficients. So this error is still, there's a part of the rounding off error here, but it doesn't matter.
So I just want to ask, this works from -1 to 1, right? Just on the interval from -1 to 1.
Yeah.
What happens if we want to do it?
Yes, this is a good question. That is what we are going to talk about next. Yes, this is a good question. We cannot stop here, right? -1 and 1, and then what if we have integrating from the 0 to 3 and 0 to 100? What happened? What happened? Yeah. So let's see. We want to take a look at the applications first, because the theorem is not so interesting. So let's take a look at another applications here. If we have a general integrals, is from A to B, and what can we do? So we want to, actually you can do some things here, and you can convert the integrals -1 to 1 to A to B. So here, let's take a look. You have already learned this before, I believe, in a calculus class or linear algebra class. You can map the -1 and 1 interval to any intervals here. If we have closed interval, and then you can map the -1 to 1 to any intervals on the real axis. Have you learned this before? You have learned this before, but if you forgot what you have learned before, let's take a look at that formula. Actually, it's giving you the change of the variables. This is the change of the variables formula here. If you take a look at this picture, it's actually, if you create, this is a B on the x-axis, and then this is the -1 and 1 on the t here. And we are changing the variables from x to t. Actually, you can do this. We can create a linear function here, and we have one nodal point here. We have 1 point here. It's A -1. And then this is B1, and then you connect these 2 points with the straight line, and then you give from the slow nodal points form, you can get the equation for this straight line, right? This straight line here. This is you can get the equations by this node point form, this one, and you can see that from this linear, this straight line, and then you will see that for the A, it's mapping to the -1, and for the B, it's mapping to the 1. This is mapping to -1, and this one is mapping to 1. And all the things in between can be, this is the some things in between, right? This is something in between the A-B interval. This is something in between the A-B interval, right? You will see that this interval by this linear function, this is something maybe let's call this is the W1, and W1 is on the AB, is in between AB. Any points any points here on this line, and then you will see that the X value is W1, and then W1 is in between the interval A and B. But with the Y value, the T value, it's mapping some things to, it's mapping some things to the, let's say this is X1, and it's mapping to this is T1, and then T1 is in between the interval -1 and 1. You will see that this, if you create a function by the slope point from the linear algebra, and then you will find out that this mapping is mapping any points x1 to the T1, and then x1 is in between the intervals A and B, AB, and then T1 is in the interval -1 and 1. So with this mapping, actually we can map the AB interval to the -1 and 1 interval. Does that make sense? So we are mapping any points here. This point is in between the intervals A and B. But if you substitute the X value here, and then you will get a T value, and then the T values is in between the -1 and 1. Does it make sense? This change of the variable. So with this, now we get the change of variables formula, and then the change variables formulas is this one. And you can also write it this way. Now what can we get is, so we are going to, what we want is to answer the question, how can we approximate this integral on the interval AB, and then so what can we do? We can change the variables x to the t, and then the t would be in between -1 and 1 if we use this formula. If we use this change of variable formula. Let's try out this. We are going to replace each x here, and we have x here, right? And then we are going to replace the x with the t, and we got this formula here. We got this. So let's just substitute the x with the t expressions. We got this d, and then 1/2, and then b minus a, and then t plus a plus b, and integrates. What about the fx? Fx we also have, let's change the fx as well. The x in between, it should be 1/2, and then bat plus a plus b. I'm not writing the limits of the integrations at this moment because we need to be very careful. We just change every x into the expressions with t variable, Now we should be very careful about the integrations limit. This integrations limit is for x, but here we have already changed the variable. We change the variable to t. And what about the limit, the range for the t? If we are using the formula over there, and now we are changing the x with the t expressions, and what is the range for the t? This is the range for the x, right? And up to the mapping, the range is between -1 to 1. Hence, we have the integrations limit should be from -1 to 1. We need to be very careful here. Don't take the AB to the next formula, because we have already changed the variable. We change the variable from x to t, and then this is the variable we care about. we are doing integrations about the t instead of x after changing the variable. And this is how we perform the integrations on any intervals a, b instead of -1 and 1. This is how we do it. We change the variable and then change it to the interval -1 and 1. And let's take a look. If you further calculate the derivative here, because this is d something t, and then if you calculate the derivative for the expressions here, and then we can extract one things out, and then that is the -1, 1, and then f to, this is just the x expressions with the changing variable, with the new variable t, and then a plus b. Because the derivative of that expressions is 1/1/2 b minus a, and then so this one equals to this one. We get what the derivative out, and then this is just the dt. This is the formulas we use to, this is the formula. This is the formula we use to calculate our integrals here. We transform the intervals a, b to the -1 and 1 with that formula, with this t equals to, x equals to something, x equals to b minus a t, and then plus b plus a divided by 2. Hence, let's take a look at one concrete examples. We got the formula here, and then and we are going to use these formulas to approximate this, to get the quadratic rule, Gaussian quadratic rule on this interval from 1 to 3. We are going to, I'm not going to let you to read these slides, and then let's try out here. Let's try out one by one. So this is the fx functions, right? And what we are going to do, we want to calculate this fx and then dx, and then so first we need to substitute that integrals, the right hand side, the purple one, and then get the equivalent expressions here. We want to change the intervals into -1 to 1, and this is our b and this is our a. So b minus a is just 2. -1, 1, and we got 2 here, 2t, and then plus b plus a, and this is the b, this is the b, 3, and this is 1, and then 3 plus 1 is just 4. And divided by 2. And we also have the b minus a divided by 2 part, and that is just the 3 minus 1, 3 minus 1, and divided by 2. And so we have 3 minus 1 divided by 2. And that's it. -1, 1, and then f, 2t plus 1 is just t plus 1, right? T plus 1. And 3 minus 1 and then divided by 2 is just 1. This low here, this coefficient can be simplified into 1. So we just write it in this way. We skip writing that 1 here. And which means that if we want to apply the quadratic rule, we have two situations here. We have n equals to 2, n equals to 3. We have 2 nodal points and we have 3 nodal points here. If we want to apply the interval here, we have So if we take a look at the table, n equals to 2, then we have, if you look at the table, we have n equals to 2, we have 2 nodal points. And then that 2 nodal points is this one, if you look at the tables above, and then for the -1 and 1 interval, -1 and 1 interval, and then you have 2 nodal points. The first nodal point is 0.5 something, 0.5. The first nodal point is 0.5. I'm just copying down something useful information from that table we just showed you. We just saw it just now. And the second nodal point is the -0.577356629. They are symmetric. So one is positive, one is negative. For these two, you have the coefficients 1. So what we are going to do, we have such values from that table. And then if we want to use the Gaussian's quadratic to approximate it, Gaussian's quadratic, and this means that we are going to use C1 and then F. But here you are not doing fx1. You are doing some replacement here. You replace the t with such a value. But in this expressions, you have t plus 1, which means that you have to substitute the t with this value. So inside the parentheses, we should have. So here we have, let's say this is a t1 plus 1. T1 is just the x1 value here. Let's replace the variable here. And then let's say this is T1 and this is T2. C2 and F, T2 plus 1. Does it make sense?
Should we make 2 plus 2? Because 2t plus 4 divided by 2.
Oh, that is 2, right? Oh, I miscalculate something. 4 divided by 2 is 2. Sorry. So here we have 2 here. Poor calculation. Does that make sense? We replace the t value with the t1 value here, and then another nodal point is it should be t2. Any question here? If you take a look at the formulas we get here, and then and also the things shown on the textbook, this is the actual calculations, and then that is the formula we get. And then we have the C1. C1, we just have the 1 coefficient here. So actually, this is 1 times something, 1 times something. This is the C1. This is the C1. And then this one is the FT1 plus 2. And this is the C2. And then this is the F T2 plus 2. Does it make sense? And the F functions is defined in this way. Actually, you need to just plug in, and this is T1 and then plus 2, and then you get such a value, and then such a value substitute into this X function here. The X function, it looks like this, fx equals to x6 minus x squared sine 2x. And then now, inside parentheses, you get such a value, and then you put in such a value into this function, and then you 1 times the values you get, and then 1 times the values you get, and then do the sum here, and then you get this. Any questions here? Any questions here? How we get the integrals on this interval. And if we have 3 nodal points, we can do the same things, but we need to use the another another table here. If you go back to take a look at the table we have, and then if we have 3 nodal points, and then on the interval -1 and 1, what can we get is we have 3 nodal points. T1 is the, let me see the T1. So T2 is the origin 0. And then the T1 should be, let me see, -7. So let's just starting from negative to positive. 0.77459666692, and then the T2, T3 here is just symmetric about the origin. And what about the coefficients? We have the coefficient C1 is the 0.5 something. 0.555555556. And then the C2 is the 0.88889. C3 is still the same because they are symmetric about the origins, and then you will see the C1 and then the C3 are the same weights. They have the same weights. And so now you still need to be very careful. And we are still using that change of the variables at the very beginning, but we are not going to. So after some change of the variables, we are still using this expressions here. But now we are going to use 3 nodal points, which means that with the Gaussian's quadrature through, and then but n equals to 3, we got fx1 and then c1 and then c2 fx2 and plus c3 fx3. And you will see the actual calculations here. We do all the actual calculations here. C1, and then we have the 0.5, around 0.5. And this is the problem here. fx2, T1, T2, T3, because we have already changed the variables to the T. And that's the T1, T2, T3, T1, T2, and then T3. Actually, it's not T1, T3, T2 here because we have, because the integral here is ft plus 2. It should not be T1 inside parentheses. It should not be T2, T3. It's not a simple T1, T2, T3 here. The integral has already changed to, it's not ft, it's ft plus 2. And we also have ft2 plus 2. We are substituting the t here. We have the T1, T2, T3. So inside of parentheses, we should have, in the Gaussian's quadrature through, we should have T1 plus 2, T2 plus 2, and T3 plus 2. And for the actual calculations, we could have such things. The 0.5 is the C1. And then the C2 here, the 0.8, it's around 0.8. It's doing some rounding off here. The 0.5 is the C3. And inside this parenthesis is just the T1 plus 2. T1 plus 2 here. And then this is the T2 plus 2. T2 is a 0, so 0 plus 2 is just 2. And this is a C3 plus 2. Any questions about the applications? And this is all the things you need to know about the Gaussian quadratures. But we will tell you some things more interesting fact about the Gaussian quadratures, how to derive it, and also we would tell you, we would also investigate into the convergence theorems about the Gaussian quadratures. But this is not something you need to master. And because you just need to know the fact, and then you don't need to know how to prove it for the requirement of this class. But if you are interested into doing some research, maybe you you also need to know their proof as well. But by so far, this is the general requirement for all the students in this class. You just need to know how to apply the Gaussian quadrature to different interval. And the next part, any question about the applications by so far? Once again, before we move to the theory part, the theory part is not a requirement part. It's not required, it's optional. But it's interesting to know, and it's also some rigorous things because mathematics is rigorous. So let's take a look at the proof part as well. We are not the engineering department, we are the mathematics department, so we need to take a look at the theorem and the proof. And last time we have already talk about the theorems. We have the statement about the nodal points, and then the nodal points are the roots of the Legendre's polynomials. And we also have a statement about the coefficient. The coefficients can be calculated in this way. And although you have the table, and then you need to know how the table, how people get that table of the coefficient and the nodal points. They get the nodal points and their coefficients in this way. So they're Legendre's polynomials, and also do the integration, and then you get a C1, C2, and the X1, X2. But in your homework and in your exam, you don't need to calculate such things. You just need to use the table. Does it make sense? But here, this is how the people use the theorem, and they use the statement there. And this part is telling you that if you use the Gaussian quadrature, and you would get the precisions, the degree of precisions is 2n minus 1. So we have two things to prove. Not two things, we just have one thing to prove. We need to prove that degree of precisions is less than 2n. And the highest degree of precision is 2n minus 1. So last time, let's take a look at what we have from the last time. From the last time we have, because we are going to prove the degrees of precision is 2n minus 1, and we are going to, first we do the basic situations, and then the basic situations is not 2n minus 1. The basic situations is the polynomials. Oh, okay. I have some misspelling here. This is the polynomials, and we have the polynomials, which is with the degrees less than n. And if we are working with the polynomials with the degree less than n, we can rewrite the polynomials with the Lagrange interpolations. And with the Lagrange interpolations, and then let's take a look at the Lagrange interpolations error. The Lagrange interpolations errors, it looks like this. We have n nodal points, and the error chance has an n derivative here. And derivative here, because let's take a look at our assumptions for the basic situations. This is the basic situations. We are working with the polynomials. And then the polynomials is with the degree less than n. And this is the Lagrange, if we are doing the Lagrange interpolations of this interval for this polynomial, and then we got such an error. This is the error term. And then the error term, we have an n derivative here. But the degrees for that polynomial is less than n, which means that if you get the derivative of the px, the polynomial here, the n derivative, and then this would goes to 0. Does it make sense? Because the degree is less than n. So let's take a look at here. Because the px is in this way. The px, in the first situation, the px is a n minus 1 x n minus 1, and then all the way to a0. And this is the highest degrees of that polynomial. This is the possible highest degree. Maybe it's x3, x2, but the highest degrees can be n minus 1. But if you take the n derivative and then this would become 0. The n derivatives for this one is just 0. And which means that if we do the Lagrange interpolations for the px, and the Lagrange interpolations exact, it means there's no error, and then we can use the equal sign. So Lagrange interpolation is used to approximate something, right? Approximate the fx, to approximate the function fx. But here, because the Lagrange interpolation, the error term here looks like this, and then the n derivative here is 0, which means that if we are going to, if we rewrite the expressions with the Lagrange interpolations, then we can use the equal signs instead of that approximation sign. So we have the equal signs here, and the Lagrange interpolations formula looks like this: the pxi, the function evaluated at the xi, and this is the Lagrange polynomial basic function. And next, this is just the Lagrange interpolations for that polynomial. But what we are going to do, we are investigating in some integrals. So what we are going to do is to integrate these things over the intervals -1 to 1. And this is what we have done last time. We do the integrations on both sides, the left-hand side and the right-hand side. The pxi is just a constant because it's just a function evaluated at the xi. And we can get the integrations inside here. And we do the integration for this part. And this part is actually what we have defined in the theorem. And this part is just the CI coefficients. And so now we can write it until this way. It's equals to the sigma sum from I equals 1 to n. And this is the CI part. And because this is a definite interval over the interval -1 to 1, so this is just a constant CI. And CI pxi. And at the end of the day, this is the approximations formula. This is the approximations formula. This is the approximations formula we get. And because we assume that the px is with degree less than n, and you will see that we have equal sign here, which means that we don't have any error here for the polynomial that is with degree less than n, and then we can approximate the integrals with such a formula, and then there's no error here if this is a polynomial less than n. And this is how we get the formula, the Gaussian quadratus rule. But the question is that this is just the polynomials with degree less than n. And what is our goal for the Gaussian quadratus? We want to achieve the highest degree of the precisions. And then the highest degrees of precisions here is, we have n nodal points, right? And then from that theorems, the very first theorems, we know the highest degrees of precisions is 2n-1. We get such a formula, and then we want to prove that this formula actually works for the up to 2n-1 degrees of polynomial. So the next part, this is the basic situations. We discover one formula, and then this is the Gaussian quadrature rule. After we do the integrations on the Lagrange interpolations, and then we got such a formula. And then, but now we need to prove this formula actually works for the polynomials with degree less than 2n minus 1. So here, so the one situation, we need to prove there's a one situation here. We already get the formula, and we want to prove the one situations. We want to prove this, the -1 px dx. So now we want to prove, actually we have an equal sign here. We have the formula, but we want to prove this formulas, it works for the px polynomials is a polynomial with degree less than 2n, which means that this is a polynomial, again, misspelling, polynomial. Once again, we have this. We say the degree is less than 2n, which means that the maximum degrees could be 2n minus 1, less than. So now let's take a look. Let's say we want to prove this. We want to prove this is actually happening. We have the equal signs for the polynomials with degree less than 2n. The equal signs, which means that the approximation is exact. We don't have any error. So now let's take a look. We assumed what we have is we have such a thing. So assumes the px here is a polynomial. In this situation, this is the polynomials with degree less than 2n. It could be 2n minus 1. And what we are going to do is to do some division, some polynomials divisions. Let's do polynomials divisions here. Polynomial divisions with the polynomial divisions, we get this, the long divisions. It's similar to the number long divisions. We get this. We get two polynomials. And polynomials. And one is the quotient. This is the quotient part, And we also have a remainder polynomial. This is the remainder one. This is pretty similar to what we have in the number long divisions. And each of the degree is less than n. And let's take a look at what we have in the general one. The general one is the number divisions, right? And let's see what we have in the number divisions. Oh, we don't have any chalk here. So let's see if we are doing the long divisions for number. We have, let's say we have 8, right? And then it's 3. You would do the quotients here. You were getting the largest quotients as possible, and then it could be 2 times 3. It's okay. If we get the 3, and then that is bigger than 8. So this is 2, and this is the quotient. And this is the divisions number here, divisor. And then 2 times 3 is 6, and then you would get a 2. This is the remainder, right? So what can we do here? And there's some things you need to be very careful. If we put a 1 here, could we put a 1 here? Is it the general things we do? No, because we want the remainder. If you have the remainder 5 and then the remainder is bigger than the divisor, and then this is not what we want. We want the remainder is less than that divisors. So remainder here, we require the remainder is less than the divisor. And the same things happening to that long divisions. If we got the polynomials, so let's say we have 2x squared plus 1. And this is our px, okay? And then if we want to do the divisions, we want to factorize this expressions, and then with x, and then you will get the quotients. The first time you will get the 2x, and then the second time, and then we don't have any x here. So let's say this is just a 2x plus 0, and that is just 2x, and then we got 2x squared, and then if you do the subtractions here, you get 1 remainder. And now you can write the px into, and this is just the divisor, right? The divisor, and this is the quotient, qx, and this is the remainder. And px can be written into the qx, and then the divisor px, and then plus the remainder rx. And you will figure out that we also require that something looks like this. The remainder is less than the divisor, but there we have the polynomials. So we are requiring that the degree of the remainder is less than the, actually you can require that it's less than the dx. But here you will figure out that the degree. So actually we require that the degree is less than the dx, the divisor. But actually you will figure out that because we are doing the divisions here, and then this is just a multiplication, and this is just the sum here, we will figure out that the degree of this 2 is less than n. So what I'm going to say is that if you are going to divide the, so it should be the quotient here. This is the divisor, right? And the remainder should be less than that one. And then the degree of, we don't have any requirement here for the quotient. But here, in this situation, actually, we have some conclusions about the quotients as well. So take a look at here. We are going to divide. So I haven't stated the divisor here, but actually we divide the px by the nth Legendre polynomial, by the nth Legendre polynomial. And then the Legendre polynomials here, we can denote it as the p and x. And one remark here, the p and x with degree n. This is with degree n. So next, let's take a look what can we rewrite it into the px, because we are investigating into the px, right? And then the px here, and then it could rewrite it into the p and x. We get the quotients, and then the p and x is just the divisor. This one is the divisor. We can rewrite it into the quotient x, and then times the p and x. And then plus the remainder x. And don't forget that we say this one is the divisor. This one is the divisor. And then from the long derivations, we require that the degree of the remainder is less than the divisor. So which means that here the degree of the QX, the degree of the Rx is less than n, because this is the divisor, and then the divisor is with degree n, and then at the end of the day, if you do the long divisions, we require the remainder should be less than n. And now, what about this QX? Why do we have the QX is also less than n? That's because this one is with degree n, right? And then this one is with degree less than n, right? And if you do the divisions, if this one is n or more than n, and then you will get the product of them. So if you have, if this one is with degree bigger than or equals to n, and then we have a problem here. If this one is with degree bigger than or equals to n, and then this one is with n, and then the product here is at least to n. And then this, we get a polynomial which is with the degree bigger than or equals to 2n, but here on the left-hand side, we have this one is less than 2n. So we have a problem here if this one is bigger than or equals to n. So the conclusion is that this quotient x, the quotient here is should be less than n as well, the degree. And this is the long divisions. And now we do the long divisions. And why do we do the long divisions here? This is because, let's see. Okay, let me erase all the things here. I don't know why we have these things. I think that's because we use more places to prove it. Okay, we do the divisions. Why do we do the divisions? Because in the basic situations we only have the polynomial is with degree less than n, right? We want to reduce these advanced situations to the basic situation. So now we do the long divisions. We want to reduce the situations to the situations where we have only the polynomial. We have the polynomial with degree less than n. So now let's take a look if we, what would happen if we do the integrations here. If we do the integrations, here, we have, so from this long divisions, this is long divisions, and we do the integrations. We integrate the -1 to 1 px, and this is what we want. We want to get the approximations formula, right? Let's do the integration, -1 1 qx, and then times the pnx, and plus the remainder. And we can separate into two parts. And the first part and the second part. -1 1 dx. And don't forget that what we have here, and this one is with degree less than n. And this is the basic situation, right? From the basic situations, actually you can rewrite this with the sigma sum I equals to 1 and then to the n with the coefficients ci, and then the r evaluate at those notables. This is the basic situation because this is a polynomial less than n. Does that make sense? This is something we have proved just now. This is the basic situation. From the basic situations, we get this. We can rewrite this quadrature rule is except for the p, the polynomials, which is less than n, with the degree less than n. And then now for the remainder this is a polynomial with degree less than n, so we can apply that quadrature rule, the Gaussian's quadrature rule, and this is an exact formula. Any questions here before we move on? Any questions here? This is a very important part. And as you can see, we, with the long divisions here, we reduce the situations to something that is less than the degree is less than n. And this is the basic situation, and then we can apply that quadrature rule here. And what about the first part? We have this is the first part, and this is the second part. And then for the second part, we can write it into the quadrature rule, the Gaussian quadrature rule from the basic situations. And then what about the first part? The first part, this one is with degree less than n. Is less than n. And what about this one? This is the Pnx. And then Pnx here is not just a general n degree polynomial. It's the Legender's polynomial. This is very important. This is Legendre polynomial. And this is why we use the Legendre polynomial to generate the Gaussian rule, the Gaussian quadrature rule, because we have the orthogonal things here. And if you forget some things about the Legendre's polynomials, let's go back to what we have in the very beginning. When we talk about the Gaussian quadrature rule, when we introduce the Gaussian quadrature rule, we have talked about a very important property about the Legendre polynomial. If we do the integrations, this is the Legendre polynomial n. And the product here is with the Px polynomial. And then this Px polynomial is less than the degree of this polynomial is less than n. And this property counts as that. If we do the product of them, the Px with the Legendre polynomial n, the n Legendre polynomial, and then we do the integrals over -1 and 1, and this is 0. This is because the Legendre polynomial is an orthogonal polynomial. And we are going to make use of this property to reduce our formulas below. So let's go back to here. So now you get, this is the polynomial with degree less than n, and this is the Legendre's n polynomial. And this is the integrations over -1 and 1, and we use that property too. This is the property two, and then these things is 0. Does it make sense? Because that is less than n, the Qx is with degree less than n, and then any inner products with the Legendre n polynomial, and it should be 0, because this is the orthogonal things. And now we can reduce all the things into, so here the -1 Px dx equals to the -1 Rx dx, because this one is going to 0, and then we just have these things. And then with that, with the Gaussian quadrature rule for the polynomial less than degree, the degree less than n, we have such quadrature rule here. We have such a quadrature rule here. Sigma n I equals 1 ci xi. It looks some things we want, but it's actually not what we want, because we still need one more step. What we want is a quadrature rule like this. We don't want remainder, because we don't want to calculate all the long divisions over there. So I'm asking a question: is this remainder of xi equals to the Pxi? If we can do this, and then this is the quadrature, the Gaussian quadrature rule we want for the degrees less than 2n. So the good news is that, so let's take a look at here. If we evaluate the Pxi, and then Qxi, Rx, Pnxi, and plus the RXI here. The good news is that, what is the XI? The XI, that is from the Gaussian's quadrature rule, right? These are Gaussian's quadrature rule. No, this is the Legendre polynomial and Legendre polynomials rule, right? Polynomials rules, which means that the Pnxi equals to 0. Does it make sense? Because we generate the Gaussian's quadrature nodal points in this way. They are the Legendre polynomial rules, and then it means that the the Legendre polynomials evaluated at the xi equals to 0, and this means that this part is actually equals to 0. This one equals to 0. This part. And because this one equals to 0, so we have the Pxi equals to Rxi. And now we finish the proof. We can say, okay, we do have such a equal sign here. And we have this one is the polynomial, which is less than 2n, and then is equals to such a Gaussian quadrature rule here. And this is how we prove that the Gaussian quadrature rule, it works for the polynomials, and then this polynomial is less than 2n. Does it make sense? We investigate into the basic situation. The basic situation is less than n. The degree is less than n. But how can we go further? And then we just use the long divisions for the polynomials and then reduce the situations into the basic situation. And we also make use of the property of the Legendre's polynomial here. And this is the proof. We separate the proof into two parts. One is the basic situation and one is the advanced situation. And then we use the long divisions here to persist further. Any questions here? But you don't need to master the proof here. But you just need to know how to apply the Gaussian quadrature rules from this lecture, from this class. Class is over. And if you have any questions, you can come over to ask me. And I have already posted, I will post the notes, the codes for the Gaussian quadrature rule. And it is one of the homework. You just need to play around with the code and then generate the result.
I wanted to ask about if I submit my homework late, what's the policy on the late submission? Is this like
Syllabus on the syllabus is
Oh, okay.
20%, but today's Thursday, right?
Yeah.
Are you going to submit it late?
Is it tonight?
Tonight,
Yeah,
yeah.
that's the thing. I have something else too, so I'm like a bit,
It's
tough on
20%.
time.
It's 20% penalty, but if you have some special situation and then it's just 1 day late or 2 day late, so it doesn't matter, and then I would
Alright.
like give you the exemptions. Yeah.
Thank you very much.
But you need to send an email to me to notify.
To be honest,
to
I'm just a bit
behind,
behind. Like, it's not like I have
Okay.
something special. I just have 3 things due at the same day. So
Understood. Understood.